the Poynting vector. Energy transport and the Poynting vector. The rate of energy transport per unit area in such a wave is described by a vector S, called the Poynting vector. The rate of energy means energy per second, and per unit. This is clear. The Poynting vector. S we define as E cross B over mu 0. We will prove it. Okay, E cross B is the direction. Okay, this is a W. What is energy per second per unit area? The direction of the Poynting vector S of an electromagnetic wave at any point gives the wave's direction of the travel and the direction of energy transport at that point. And SEB here are instantaneous values. The energy associated with the electric field is exactly equal to that of magnetic field. You see, this is the energy stored in the electric field per unit volume. It's defined by half epsilon E squared. We learned from previous section. And you see this E. E is C at B. Okay. And we see the C, omega 0 C. C is square 1 over square root mu kt. Okay, and then we do this one square, you get this epsilon 0 cancel out because the half b square of mu 0. And this is what? This is the magnetic energy unit per unit volume. So we see, okay, that energy associated with electric field is exactly equal to the magnetic field. They are equal. Okay. Poynting vector. The rate of energy transport per unit area. Look at this one. This is the energy transport per unit time per unit area. Now we look at this as a direction of the wave transition. Okay, we look at this. This is a square. Unit 1, so the area is 1, and this long is C. So what is this? This is in 1 second through 1 unit area, the energy go in. Okay, so this energy stored in this volume actually is the energy per unit time per unit area. So this one. Okay, this is 1. Okay, now let's calculate how much energy stored in this one. This should be in unit volume. You have UE plus UB, and the total volume is 1C is C. Okay, then we put this one, and we know UE equal to UB, so this is the UEC then C. Okay, yeah. What does UE? UE is half epsilon E squared. That's equal to E squared epsilon theta C. You know that epsilon C equal to 1 over C mu 0, because C equal to 1 over mu 0 E0 square root. So we put this one here. All right? And then what we find, this E equal to EB mu 0. This is a Poynting vector equal to this one, okay? And E over C is B, okay? It's C over B. And we found Poynting vector S equal to EB over mu 0, or E squared over C mu 0. This is instantaneous energy flowing rate per unit area. That means the energy per unit time per unit area. The intensity of the wave I, or the average energy transported over time per unit area, is equal to average Poynting vector And this one equal to E squared of which divided by C mu. What is E? E equal to EM squared sine M squared. Okay, average over C mu. This is a constant. Sine square average equal to half. So we got this one. This is the 1/2 cm. That's what is it? We look at this one. E square over half is the E root mean square over C mu square. Okay? Variation of intensity with distance. Well, we have a source S, okay, radiate wave energy. If we look at this, check at a point R from it, the energy, the wavefront is a spherical shape, okay, surface. So the total energy divided by the sphere area, the point source emitted the light isotopically with equal intensity in all directions. And then in this direction, the I is energy per unit time per area. P is the energy per unit time, the power, and divided by the area of the sphere. This is 4 pi r squared. That's the intensity at distance r for our point source.
Light from a distant source appears much dimmer than light from the same source seen up close. We'll use this small filament light source and a photometer to demonstrate how the intensity of a light varies with distance. The photometer measures the intensity of light falling on its sensor. When the photometer is 40 centimeters from the light intensity reading is 0.41 lumens. If we double the distance, the intensity is 0.10 lumens, or about 1/4 of the original reading. What will the intensity be at 3 times the original distance? At 3 times the distance, the light intensity is 0.04 lumens, or about 1/9 of the original reading. This graph plots the intensity of the light measured at the 3 distances.